So my background is experimental plasma physics and controlled thermonuclear fusion, and my career subsequent to that is mostly systems engineering. Recently, there's been an excitement about fusion because there are big things going on in the south of France and smaller things going on in places as local as Devon's here. And these are going to change the way we perceive energy generation, I think. This is the basic outline of part one. Part two really is a lot about starting with essentially number 5 on that list, because we want to talk about enough about how all this stuff works so that when we get to talking about how it really works, how you make it practical, we don't have to do all this. So that's what the purpose of this talk really is get people up to speed with the basic ideas that govern how fusion works. So I want to deal with it from the standpoint of a couple of things. First, I want to talk about fusion in terms of the definitions and sort of working examples. Then I want to talk about why it's important. And then we're going to go back sort of to this again, but at a higher level of detail. And we may get to the brief dive into nuclear physics, and we'll dive into it very, very briefly and very, very briefly on confinement. The basic idea of this whole thing is, what is it? Fusion is basically a nuclear process, and you always have at least 2 and maybe have more nuclei combining to form one or more nuclei, and there are sometimes other subatomic particles that are involved. The reason why everybody's interested in fusion for all the different applications, from the stars to terrestrial to stellar drives, is that the difference in mass between these various things that come together, and we have a lot of terminology in fusion that it's very sophisticated terminology. So we call it goes into and goes out, which is the products are the goes out, and the in reactants are the goes intas. And the difference in that mass using E equals mc squared is energy that's released in some fashion. Sometimes it's in the form of photons, and sometimes it's in the form of charged particles, and sometimes it's a form of neutrons, and there's also neutrinos and stuff involved. Fusion powers stars in their main sequence, such as the sun, and also other parts of the stellar families that involve bright stars. The very dimmest stars are really just kind of cooling objects, and they don't really matter to it. Fusion is responsible for the majority of the elements in the universe, because the Big Bangs probably only mostly contributed 3 elements, the vast majority being hydrogen, some helium, and a very, very small amount of lithium. All the elements that we're familiar with, basically 94 roughly terrestrially occurring in some fashion, are a product of fusion. A lot of it is produced in stellar cores up to a certain mass, and then beyond that mass, it's produced in collapsing stellar cores, and the really exotic stuff like platinum and gold and things like that apparently are produced by colliding neutron stars, because even the collapsing stellar cores don't have enough time and enough neutrons to to synthesize the really heavy elements. So fusion can actually be endothermic. That's not all that exciting from the standpoint of trying to make energy, but it's important in a sense, because that's how it governs the final lifetime of stars in various ways. And it can be exothermic. And we're only going to talk about exothermic because basically, well, if you don't make energy net, you're not really of much interest if you're trying to generate electricity. Stars and nucleosynthesis both involve thermonuclear fusion. So does uncontrolled fusion, aka the AKN the bomb, thermonuclear bomb, hydrogen bomb, and controlled thermonuclear fusion, of course, which is our object of this thing in the long run. So this is kind of the sort of one view of fusion. Apologize, there's a couple of equations that appear in this thing, as well as there's some sort of fusion formula. I try to minimize those, try to stick with mostly graphs and stuff, but pictures too. So when you basically start to look at the entire periodic table, you can essentially plot the entire periodic table in a number of different ways. The most common way we plot the periodic table is with electrons, because that's what we interact with. But there's also nucleons. And for any given element, there are a number of protons in the nucleus that determine that to be the element, because that number of protons sets the number of electrons, which then the various shells make the chemistry which we're familiar with. However, there are also in the nucleus neutrons, which don't contribute to the element per se, but they contribute to the stability of the element. So we have elements that start out with very, very simple things like hydrogen. That's down here in this lower corner. There is one in the form of protium, or common hydrogen. There's one nucleus in the nucleon in the nucleus. It's a proton, and it has a very low binding energy, obviously, because there's nothing to bind to. As you start to make the nucleus a little more complicated, you move this way, number of nucleons in the nucleus, and you move this way. So helium basically is up here at the same point as this in terms of the number of protons. You have deuterium. Deuterium is heavy hydrogen. It consists of a proton and a neutron. So if you draw a line down here, this would intersect it too. It needs some binding energy, obviously, to hold it together. And that's provided by what's known as a strong nuclear force. The neutron and the proton stick together, even though they don't have an electrostatic attraction, the neutron being neutral. As you go up in this curve, or you go this way, you intersect this point where you have helium, and you also have essentially at the same number of nucleons, you have also called tritium, or radioactive hydrogen. You'll notice there's a difference between helium and tritium. That difference corresponds to the fact that when this decays, it becomes this. And this is the energy of the beta particle that's emitted in the process of going from being tritium to being helium. That's really sort of the inverse of the fusion process. And it's relatively rare in the low atomic numbers. You go further up here and you reach this point where there's a little peak. This little peak is the alpha particle, or the helium-4 nucleus. It has the same number of protons as this helium does, but there are 2 neutrons. And it is fairly tightly bound. In fact, it's as tightly bound as it's going to be for a while. There's a drop down, then you get to lithium. That's relatively important that there's this difference in between these two and this one. And then you start climbing again. And as you climb, you start to cross a boundary that's kind of an important boundary. This energy per nucleon, everybody's familiar with million electron volts. Is that's not bothering anybody? Is that okay? Yeah, because I can converted into temperature if people want to hear, Kelvins and whatever. Okay, so at this point, you start to hit carbon and oxygen, and you're still going up in energies per nucleon, but it's dropping off. You're piling on more and more neutrons, and they're sort of making this thing stick together better without needing nearly as much to overcome the electrostatic repulsion. So the problem with going from hydrogen to helium is that now with two protons, the two protons fly apart. If it wasn't for the neutrons basically providing the sort of the relevant material to allow the nuclear force to pull it together. So there's a constant kind of a boundary balance between electrostatic forces trying to take it apart and nuclear force trying to pull it together. Keep on climbing, and eventually you get to this point where there's an absolute peak. This absolute peak occurs at iron, 26 protons, 56 nucleons. So there's 30 neutrons. So you're already starting to see that you're increasing the number of neutrons past the number of protons. When you get to this point, you reach the absolute peak in the terms of the average binding energy per nucleon. There's another slight peak over here with nickel where, because it has a slightly larger number of protons involved, it's almost a flat spot. Then you start to decline as you add more and more protons and more neutrons to stay relatively stable. Eventually you get to the point where you aren't going to be stable. That's basically in this region over here, and this is where you find the heaviest elements that occur on the Earth, or pretty much in the universe. From the standpoint of what we're interested in, making energy, stick things together up until you get to make iron, and then you're no longer making net energy. You're going to see a number of different terminologies that are used, some by the nuclear science and some by the plasma people and some by the thermonuclear energy people. And some of them use, unfortunately, the same letters. And I've changed in some cases to make things a little more transparent, but in some cases I've left them the way they are. So the energy that's released in the reaction is capital Q in this particular plot, table. You'll see another use of capital Q is the total energy being released by like a fusion reactor, and those are not to be confused. So the simplest fusion is two hydrogens together to make one helium. That releases a 1.5 almost MeV. On the other extreme edge of relatively easy to achieve fusion, you take a helium basically, and I'm sorry, this is sort of mislabeled in a sense, because this is on its way to being a helium. It's really not yet the helium because there's some decay processes involved. This is really what happens in the sun. This is basically the reaction right here. These two are the people started thinking about these originally in terms of terrestrial uses. And in fact, they do some of this in nuclear weapons. But for terrestrial uses today, we're mostly thinking about this reaction where we have a deuteron and a triton, and we combine them together. We make a helium alpha particle and a neutron. excuse me, not the most energetic. The most energetic is this helium-3 and lithium, which gives you 2 alpha particles, a proton, and releases 22 MeV. So now we'll talk a little bit about astronomy, because this is how we first understood fusion and how it's still relevant to our understanding of how we do certainly inertial confinement type fusions. This is a famous Hertzsprung-Russell diagram. Hertzsprung was a Norwegian who was working in Germany and early 20th century. Russell was doing essentially much the same at Princeton. Oops, sorry. And both of them had taken what was called the Harvard classification of stars. Harvard published this in 1901, and it basically looked at the spectral classification of stars and compared them to their brightness. This is real data. This is 20 some odd thousand individual stars that have been plotted on this curve. And there are several curves. One curve that's most interesting to us is this one that's called the main sequence. And in the middle of all this essentially is the sun. Somewhere here, I guess. You'll see it. You know. This is brightness over here. The sun is equal to 1. Yeah, so I guess it's over here. The sun is right over here. And this is a measure of essentially temperature. It's a color index comparing blue and violet temperature color filters. And it also gives rise to the famous spectral classification, which when I was a little kid, you could say it. I don't know if you can say it now, it's politically incorrect, but I'll say it in any event. Oh boy, a fine girl kissed me. And now it says right now, sweetie. There's some others added in here that weren't on this original plot and then don't fit this data set. When you go this way, you're getting very hot, and you go this way, you're going down in temperature. And here's the sun. It's a G-class star. So you draw this line down here and you hit this thing, and somewhere around there's the sun. Now, another version of the same thing, basically. Absolute magnitude this way, spectral classification, or temperature this way. So here's the sun. It's a main sequence star. It's constructed of what we see, that's the photosphere, and corona, which we can see during an eclipse. And then inside it, there are different layers of the way the energy comes from the core outward. All the energy in the sun is created right here in this very small core. If you think about the dimensions of this, this is sort of like 1,000,000 kilometers almost. And this core is not much different than the size of the Earth. There is immediate transport of energy by means of radiation. And in that phase, basically the gamma rays that are released in the core basically propagate outward, dropping down in their photon energy as it spreads, the energy amongst more photons. And then you get to a point where you start to become in equilibrium between the energy of the photons and the thermal energy of the motion of the material. And that's known as the convection zone. And then finally, the photosphere where the light comes to the surface, comes out, and it's mostly visible light. There's some ultraviolet and it's infrared. Before we disappear from this, the reason for the dimensions of this thing is the balance. The energy is produced here and in the form of the various transport means. It exerts forces on the matter that balance the force of gravity that's trying to crush it. So stellar classifications can also be looked upon in terms of the size of the stars. are commonly associated with these classifications. So the really hottest stars actually quite large. And that's because it takes a lot of mass to get the temperature up hot enough in the core that you can, in fact, provide the higher energy photons at the surface. Down in the really low temperatures, things get really small, and these are just marginal from the standpoint of actually being able to be visible. The emission primarily is in the infrared. By sort of an aside, the new telescope that's just going to be operational in a few weeks, we'll be focusing really on this area around here and stuff. The few equations. So the temperature is basically can be computed from the brightness, or the brightness can be computed from the temperature by what's known as the Stefan Boltzmann Law. This is a 19th century statistical mechanics type of calculation. Two different people involved, Stefan and Boltzmann, and the work basically led to this relationship. And you notice this huge power law. Power laws are going to be very important in understanding fusion. So here is the fourth power of the temperature. And this is the square of the radius, or the surface area. Right. There's also something called the mass-luminosity relationship. This was developed empirically in the early 20th century. And it relates to this little weird circle here as the sun, given this way over here. So the brightness versus the brightness of the sun is linearly connected almost to the mass. Turns out for a wide range of stars, this A is roughly the same. It varies by a factor of 2.5 or 3 over almost 2.5 to 3 orders of magnitude of changes in mass. For the sun, it's actually the closest fit is 0.78, right? Similar stars to the sun. And it relates to the energy generation in the core and is roughly proportional to the star's inner temperature. The dirty secret of fusion on the Earth is that every kind of fusion we do on the Earth, the sun is colder than we are, even at the core. And that's because gravitational confinement has its advantages in some ways. So the rate of generation of energy in the core is basically measured in generation per unit mass, and it's strongly dependent on temperature. In fact, it's proportional to temperature to the 15th power, which you'll almost never see anywhere. A number where the power law that's strong. This governs stellar stability because it's that balance between gravitational and the pressure outward. So if you have too high a temperature at the core, you'll get instability from the standpoint of the star won't stay together. And if it's too low, it collapses. So going back to the nuclear stuff again now, the binding energy per nucleon is empirical also. There are lots of theoretical calculations, but they don't quite fit exactly what we measure, right? But they're not too far off. So the typical binding energy per nucleon is this complex expansion where the first term is just the number of nucleons, neutrons and protons. The second term is the 2/3 power of that. These various coefficients relate to the different ways of calculating this thing in terms of what's known as the liquid drop model of the nucleus. And then it gets into fractional powers and keeps on going. When you plot it, this is a result of doing this calculation with supercomputer relatively recently. This is not a perfect fit to the observed phenomena, but it's not terribly far off. And you'll see that in the number of protons, so there's iron. That's the center of this bullseye of this contour map. So iron is right there. And again, 30 and 2656, that's center of all centers. And that corresponds to 8 plus MeV per nucleon. So this is calculated based on something called the Bethe-Weizsäcker formula. This is two people, Hans Bethe and Bernard, I think, Weizsäcker. And they did work before supercomputers when you had to do it all by hand. And the net result is, this again is a supercomputer plot. This is what they based their work on, and this sort of combining these pieces together. So stable nuclei occur pretty much along the center line of this thing. You start to get kind of flaky around the edges over here. So let's look at the physics of nuclei a little bit. There are 94 naturally occurring elements on Earth. This is somewhat controversial, but because we know of 92, obviously. But neptunium and plutonium have been not actually observed directly, but their decay products have been found in a couple of naturally occurring reactors where there was uranium and there was enough water that carried enough deuterium in it to basically moderate this thing as a natural reactor. This occurred in a couple of places in Africa, maybe one other place in the world. As I said, still somewhat controversial as to whether there really is any naturally occurring amounts of, maybe in the core where there's assumed to be a lot of uranium. The decay of the uranium also produces neutrons that can force some of the other uranium into the becoming neptunium and plutonium. But yeah. So the nucleus contains a number of protons that defines the element. And then you vary the number of neutrons, and that gives you an isotope of it. The hydrogen nucleus has just one proton. These are the other two isotopes of hydrogen. Deuterium or heavy hydrogen, a proton and a neutron. Tritium, a proton and two neutrons. The helium nucleus comes in two flavors, two protons and two neutrons. That's the most common form, or rarely one, much less common. The deuterium, incidentally, is about 5,000 times less common than protium or normal hydrogen. There is no naturally occurring tritium to speak of. There are obviously radioactive decay is occurring all the time. So tritium is being produced, but it has a short half-life of about 10 years. So it's going away very fast also. The reason that fusion is interesting is this so-called mass defect. Einstein basically discovered this when he discovered the equivalence of energy and mass, and she published in 1905, the famous E equals mc squared. And the mass defect is the difference between the mass of the things that are in the gozintas and the mass of the gozoutas, or in this case, the constituent particles of the nucleus, for instance. And here's an example. If you take helium, about 0.8% of the mass is reduced from what the four hydrogens that would come together to produce it. that can basically translate into a lot of energy. So quickly, fusion energy is released by putting them together all the way up till you get to iron or nickel. Fission, heavier nuclei is released when you rip them apart. We do fission right now in 100 nuclear reactors around the United States, and about equivalent number outside the United States. Very light elements fuse easily. As you get up that curve, it's harder to fuse them. Very heavy elements fission easily. And again, iron is really the reason for supernova, because once you've fused all the way and you start making iron, you're no longer making energy in the center of the star. So fusion in the sun is predominantly driven by this basic reaction. Protons come together, overcome this electrostatic Coulomb repulsion, get close enough together, they get bound by the strong nuclear force to form a deuteron. And that process leads to the production of two other particles to balance the ledger books. One is a positron, or positive electron, and the other is neutrino. The neutrino we can detect in our neutrino telescopes. It comes pretty much unmolested from the center of the sun. This instantly finds an electron, boom, annihilation occurs, and you get gamma rays. Everything we see coming from the sun in terms of energy from the sun, except the neutrinos, is the result of what starts out as a gamma ray at the core of the sun. So this process occurs predominantly by this means, leads to the production of helium, and along the way emits gamma rays and neutrinos. Right. There's also this process. It's much less prevalent in the sun, but it's responsible for about 1% of the energy. And this is present in stars that are bigger than the sun by factors of 1.5 to 2 times. And it's a catalyzed kind of version of this. In the sense, you take the same 4 protons in there, but you use carbon as the catalyst. Obviously, this only works if you're made carbon. If you haven't made much carbon, you haven't brought in any carbon, this isn't going to work very well. More details, I'll skip this. It's just complicating chains of things. So these are the different cycles. It's very strongly dependent on temperature. So a lot of things in controlled thermonuclear fusion, or uncontrolled thermonuclear fusion for that matter, you'll look at logs of things. So this is the log of the energy generation versus the log of the temperature. And you'll notice that if you're way out here, you're mostly using this thing called the triple alpha cycle, which didn't bother to show because it's non-existent for the sun. The CNO cycle, or this catalyzed carbon thing, a little bit of this comes out of the sun. You can see its curve actually goes down and below here. And so it does intersect, but the vast majority of the energy is coming from this proton-proton chain. Here's the core of the sun. Density is about 150 grams per cubic centimeter. It's about 150 times the density of water, or 10 times the density of lead or mercury or something like that. Pretty dense. The power density, however, of the fusion process, this doesn't happen very often, right? These collisions overcoming that Coulomb thing is very rare. And so the actual core of the sun doesn't produce very much energy per unit volume. About 300 watts per cubic centimeter is comparable to the power output of the human. I'm sorry, per cubic meter, not per cubic centimeter, per cubic meter. And that operates at roughly at a temperature of 15 million Kelvin, which is this point right here. Terrestrial energy from fusion. This is a recent supercomputer plot of turbulence in a spherical type of tokamak. Nobody's actually built one of these that operates at the fusion parameters range yet, but this is a prediction of what it might look like. If it did work that way, Department of Energy is promoting work in this area at the kind of early stages. And University of Wisconsin has been involved with that kind of thing for quite a while. A few other places. So terrestrial energy from fusion, now we're looking at, in this case, reactivity, which is reaction rates, basically in a volumetric fashion, and temperature in kelvins this direction, or in the log scale. This is expanded out to temperature in billions. So we're looking predominantly at this blue curve. Now, realistically, we take advantage of this curve. Really, we should be out here, but that's a really hard place to get to. So we're more likely to be operating right around here, which is not at the peak of the curve. But you have to remember, and I had a plot, but I took it out, of the distribution of energy of particles given any kind of a normal distribution, so a Gaussian-like distribution. Out in the tail, there are particles that are moving much faster than the average. And those are what are really going to be important for fusion. People would like to do these other kinds of fusions, but they need much higher temperatures. This one's still rising when you get out to billions of degrees. This one peaks, again, roughly 1 billion degrees. This one is nice because there are no neutrons involved, or very few. So here's a different way of looking at these same things. And so the deuterium reaction, which is what everybody started with playing with, for one reason, because it doesn't involve having to deal with radioactive tritium. For several reasons, that's unpleasant. One is it makes things radioactive when you get a lot of neutrons. The neutrons are more energetic in the tritium reaction than they are in the deuterium reaction. And tritium is also hard to come by, and nowadays very hard to come by because of the paperwork you need. We used to have some at the Museum of Science, but once it ran out, you couldn't get any more. So deuterium, basically, you start with deuterium, another deuterium, you make a helium-3 nucleus, a neutron, and the neutron carries off most of the energy. Deuterium has a second branch, almost equally likely to occur. It makes, instead of a neutron, it makes a proton. And there are neutrinos involved in these things, but in any event, roughly the same amount of energy. The one that everybody has really chosen for the current period of time, in any event, is deuterium-tritium. This basically produces one neutron, much more energetic neutron. Again, it carries away most of the energy, a somewhat energetic alpha particle. The neutron in this case carries away 14.1 MeV, and the alpha particle left over 3.5 MeV. In most of the way people are looking at engineering a fusion reactor, the neutron is the way you're going to extract the energy. You need this really to keep things going. And so you're looking at this moderately energetic neutron. It comes out, it will make some things radioactive, but it's also important because it breeds tritium, which is important because the tritium doesn't occur naturally very much. The helium-3 reaction is over here. I won't bother going into the detail. So this is the most important thing. This is what I heard back essentially at the beginning of this fusion era for me, was the quote that a gallon of seawater would produce as much energy as 300 gallons of gasoline. Now, that statement presupposes you don't have a problem finding lithium, because as we can see from everything we've been doing so far, there is no tritium. So you have to make it. So if you make it, the most common way to make it is to breed it with neutron bombardment with slow neutrons, lithium-6, and a neutron gives rise to a helium, a triton, and 4.8 MeV that's carried off by these two. But lithium-6 is only 7.4% of natural lithium. It's much more prevalent than deuterium is with respect to regular hydrogen, but it's still fairly rare. On the other hand, there's probably enough lithium in seawater to keep us going for tens of thousands of years. You have to, of course, process seawater, extract it. If you don't do that, if you dig it out of the ground, it's nobody's really quite sure how much there is, but it's probably quite a bit also. And it's maybe a little easier to get it from seawater than it is from digging it up after you find it. They're really popular ore bodies. People are pouring a lot of money right now into lithium mining, not just for fusion, obviously, because it's needed for batteries as well. With fast neutrons, if you have fast neutrons, you can breed tritium from this much more abundant lithium-7. The fast neutron, this neutron is fast enough, but the question is, when it gets to the breeding point, is it still that energy neutron? It produces a slow neutron, which can then breed additional tritium if you have a mixture of these two isotopes. So essentially a slightly enriched version of naturally occurring lithium, say 20% lithium-6, you can have a breeder, right? There's also uncontrolled inertially confined, same thing. Equations are exactly the same. The experiments that are done at a place like Lawrence Livermore, always they have two sets of targets, one set of targets for the people who are able to walk in with a clearance, and the other set of targets that they can show people who don't have a clearance, because it's the same basic process using a fusion bomb as you do in a inertial confinement fusion. In the one difference is that in the case of a bomb, you use a fission bomb to produce the X-rays, which are going to ultimately compress the fusion fuel. And in the case of an experiment in the laboratory or potentially in a production reactor, you would use lasers to produce the X-rays by producing a plasma and heating that plasma with the laser beams to the point where it emitted X-rays instead of using the fission bomb. Some people said you could make a bomb that didn't have a fission bomb that way too, and that's been talked about, but I don't know for sure if it's ever been done. Everything else is the same, the business of the tamper and all that kind of stuff like that. This is a couple of examples. This is the Mike experiment as part of a bigger experiment called Ivy that was conducted about 70 years ago now in the Pacific by the United States. It's the first time that a fusion reaction occurred on a large scale on the Earth. This produced, incidentally, about 10 megatons, 1,000 times the output of the Hiroshima bomb. It's another view of it from the air. There was a picture here. I have it somewhere, but I lost it in the process of putting this thing together. and that's called the Tsar Bomba. The Soviets dropped a bomb from an airplane as a test bomb. It was 50 megatons. And that's the biggest boom that we've ever made by humans on the Earth. This recent explosion that occurred in Tonga in the Pacific because of a volcanic explosion was comparable in scale to that. On a much smaller scale this is the National Ignition Facility at Lawrence Livermore. There are 192 laser beams that come together and crush a little target pellet and produce a very small amount of fusion by comparison. The basic idea of how all this worked came about from Arthur Eddington, who gave a talk to the British Association in 1920, and he said, we finally understand how the sun is able to power itself. This speculation for this began in the ancient Greek period of time, when Greek philosophers estimated how big the sun would have to be to produce the amount of heat that it was producing on the Earth. It was, pretty good for the time and period. They had some issues with it because it wouldn't really look like it would last. One estimate was it would be a lump of coal the size of the Peloponnesus. In the 19th century, with the understanding of thermodynamics and statistical mechanics and electromagnetic theory, the speculation was that the sun was just shrinking. But again, it wouldn't last long enough. So finally, with spectroscopy coming along, people could start to look at what the sun was made out of. And that led Professor Eddington to come to the conclusion that it was this reaction that occurred. Hydrogen gives you helium. And then, well, he didn't know about the positrons so much, but the positrons basically are captured to balance the equations. And when you do all that, you get this remarkable information. This is a presentation from Princeton Plasma Physics Laboratory. That's the little logo down there. 1.008 kilograms of hydrogen will convert itself to 1 kilogram of helium, and 8 grams or 10 to the 14th joules of energy, 7.5 times that. And as they said, this will supply you with all your energy needs as for about 10,000 years. 1 kilogram of hydrogen. That's why we want to do fusion. So the need for it comes about. Let's wrap up quickly here. We need energy to be available in a compact fashion. These diffuse sources of energy just don't work well with our electric power grids. Fusion can deliver in urban environments because of the lack of real problems with radioactivity, whereas fission pretty much has to be out in the outskirts. And we'd really like to be able to replace these coal-fired power plants and even maybe the natural gas-fired power plants in our urban environments with fusion. Can do that. It eventually also enables spacefaring, as we can really start to move at really high speeds, not possible with chemical reactions. And it's available on demand, basically, which is something that these so-called green energies outside of nuclear types of energies are not available. Natural gas is available, but has its non-green component to it. And it also, because of that number that we talked about, you don't need very much fuel. So again, this sort of summarizes everything that we need to know to get ready for next time on this one slide in a sense. So this is the pushback that occurs from sliding one proton against another one, or one deuteron against another one, or one triton and one deuteron, all the same pretty much, except for a little scaling because of the mass differences, but it's the same charge. Out here, basically, you've got to climb this hill. Once you climb the hill, though, the strong nuclear force grabs this thing and pulls it together quickly. Fraction of a nanosecond. And the well is fairly deep. However, the reaction rates are still going to be small unless you get to really high temperatures. So again, this is in Kelvin, but that translates 10,000 degrees Kelvin is 1 electron volt. So 100 million degrees Kelvin is 10,000 electron volts. So up here somewhere, basically, you can get a reasonably decent reaction rate. Even in this region out here is not too bad. The power that comes out in fusion power is strongly dependent on this term right here in terms of scaling of confinement. This is all magnetic confinement. We're going to talk about this next time. This is the pressure, plasma pressure in atmospheres, and that's directly related to the magnetic pressure that confines it. But if you take this number, say around a couple of atmospheres, you can see you can make megawatts per cubic meter. So that satisfies that compact energy thing. This is sort of one view of how to do it overall, in the sense there's your deuterium and tritium coming together. It comes out the alpha particle. You need that to be retained by the confinement system. And then a neutron comes flying out there. It breeds with this lithium-6. It breeds your tritons. And as Princeton says, you could pump the water in the ocean through a filter and extract lithium for 30 million years. Don't know how much exactly is present in the Earth terrestrially, but it should be substantial as well. So to make things work really well, you need this very high temperature plasma. The plasma is both a good and a bad. The good is that everything is charged particles, so you can act on it with a magnetic field. The bad is that somebody described plasma confinement as trying to pick up jello with several rubber bands wrapped around it. The lower energy state is with the rubber bands on the inside and the jello on the outside. We want it to be the other way around. Pressures involved, again, at this kind of temperatures and stuff, the pressures involved, 1 million atmospheres. You're not going to do 1 million atmospheres with anything except for magnetic confinement. And stability-wise, this quantity beta tells you the stability of the system. The pressure over the magnetic pressure is beta. It's limited to how much you can do that. And so the fusion power then becomes limited in terms of the beta and the strength of the magnetic field. This is important right here, this B to the 4th, because that's the difference between this enormous thing, the largest engineering project currently underway in Europe, which is the International Fusion Experiment in south of France, and the small little machine that you could essentially put inside of an ordinary warehouse that they're building in Devens. And that's because their magnetic field is stronger enough that b to the fourth makes a big difference. So that's it.
Thanks, Ted. So whose brain is not full? We have some time.
Okay.
Yes.
We have a, how does this questioning process work?
Well, Dick has his hand raised, and
I
so
see
does
two
Carl,
hands raised. Yeah.
So we'll take it in that order. So
Okay.
Dick,
Are you managing that part of it, Peter?
yeah, I'll try to. If I make
Okay.
a mistake, please excuse me.
All right. No.
Dick, you're up.
All right, thanks. Out of curiosity, what's your feeling about what was called cold fusion? And where do you think that's going to go, if it is going to go anywhere?
Yeah, cold fusion is interesting. Obviously, it gets back to this business of this. To overcome this, you can do it by banging things together hard, or potentially you could have other forces acting like in a solid lattice of something or other. So cold fusion happens. It's some sort of a process. I think it's real. There's no question about it. I was sort of there in a little small scale when I was at Lincoln Laboratory. We were asked by the DOD after the Pons and Fleischmann stuff came out whether or not this was worth pursuing, and we looked at it real quickly. MIT was doing some work, and there was a lot of sort of scatter in the data from different people doing different measurements. It kind of fits the classic model of the, again, politically incorrect, the blind Indian guys and the elephant. One guy grabs a tail, and he says, "Oh, it's a vine." One guy grabs a leg, says a tree. One guy grabs an ear, I don't know, it's something or other. And then one guy grabs a trunk, it's a snake. Well, no, it's an elephant. The question is, what were we measuring? And we did see some nuclear products in some of the measurements. We saw thermal energy, and we saw various electrochemical things going on. So my sort of personal speculation is that what's going on is the lattice is being loaded by some sort of electrochemical process. And then there is some sort of a nuclear process, though it's probably not classical fusion, that is allowing some of the stuff loaded in the lattice to overcome this this Coulomb barrier and get into the place where we produce things in with the strong force in some fashion. So I think it's real, but I think it's a long ways away from being practical. There was a conference at MIT, I think, maybe 2 years ago, and I went to it. I didn't participate in presenting anything. I just watching and listening. And,
my turn?
I guess so, yeah.
Yes. Yes. Okay. So, what do you think are the prospects of the work of Devon's, Commonwealth Energy, whatever,
Yep.
producing true net energy production in the next 5 years?
I think very good. The basic physics, we're going to talk about confinement type stuff next time, but the basic physics has been essentially tested over the course of that 50-year window of time. The problem has been, two things. One is from a pure engineering standpoint, how do you actually tap the energy in a useful fashion? And that really involves this business with making the reading and also capturing that neutron in such a way that when you capture it, you get the tritium, and then this energetic helium that comes out of there basically can provide you some thermal energy that you can then, use a steam turbine. So the result of that is that part has never been done because we haven't been able to make very many of these. And then the other problem is that where we have been making some of these, obviously this makes things radioactive, and it makes the research device less useful in some ways. If you're a graduate student, you really don't want to see a lot of neutrons because you have to wait to come back to take your piece of equipment and fix it or something like that. You might have to wait 2 or 3 months before it's cooled down enough, radiation wise, so you could take it off the machine. And then that just delays how long it's going to take you to get your degree. So that's one aspect thing. And the other one is, of course, that from the standpoint of everything we've done, with the exception of the last couple of years, has been with copper magnets, either cooled by water or in some cases cooled with liquid nitrogen, but in any event, a non-sustainable way of making the magnetic field for a fusion reactor, because you have to take care of that dissipation. So you need to go with a superconducting magnet. And the limits on superconducting magnets put the screws to this whole process because of this business of that. There was a limit how strong you could make a magnetic field in a superconducting magnet. And so that forced the design of this thing that is going on in south of France, ITER. It's an enormous machine. And I don't think it's a commercially viable machine. It's so big that, it's too big. But in the last 10 years, people have figured out how to take the invention that was earlier, 10 years earlier or so, of high temperature superconducting magnet materials and make them into practical materials to make magnets. So people are now making wire that you can wind into a coil of high temperature superconducting material. And we'll talk about that the next time. And that basically gives rise to a much stronger magnet, a much smaller machine. CFS has their goal to build a prototype machine that will produce net thermal energy inside the next decade, build it in the next 5 years and operate it. Obviously, the first operation probably would be with no tritium, so you can not have the problems of the radioactivity when you're fine-tuning things. But eventually, they buy the tritium from the Department of Energy and put it in there and crank it up and produce net energy. ITER will do the same, produce net energy, but ITER, I don't think, can lead to a functioning power plant. The CFS thing can then be scaled a little bit bigger, and they believe they can essentially build them in a factory in Devens and ship them from there, starting perhaps 10 years after the first net positive energy release. So I think there's a very good chance that in the decade to come, we will be really, really close to somewhere between Enrico Fermi in the squash court, I guess, in Chicago, and the two reactors that essentially came online commercially almost the same time, the shipping port reactor in Pittsburgh and the Yankee Atomic in Row, Massachusetts. Those happened about 17 years apart.
Tony?
Ted, you may be talking to us about this next time, but in your next to the last slide, 29, where you have that energy plot, building a nucleus. With respect to this curve, how does the 20 Tesla magnetic field magnitude works out? Namely, is it something that essentially drops you into that big well? Can there be an analog representation of what that magnitude has accomplished? And where was the previous step over the previous 50 years that we were constantly getting closer and closer, but never close enough?
Right. Well, we actually, in 1997, the Joint European Torus that's operated in the Culham Laboratory in England near Oxford, they actually produced a fair amount of fusion power for a short period of time by accident, in a sense, because they weren't breeding tritium or anything like that. They put tritium into the thing. Their machine, though, used a copper magnet, so obviously the time that you could keep it running was very limited. But it was pumping out, quite a bit of power, not enough to compensate for the power it took to put the plasma together. But that's where things sort of sat. And for the next, basically almost 20 years, there was almost no change in the numbers because of that problem with the copper magnets. And while there were other kind of tweaking of parameters, so for instance, the Alcator CMOD machine at MIT achieved a higher pressure because it was a higher magnetic field than the machine at Culham. But it was, again, severely limited by the fact that it had the copper magnet. And essentially the Spark machine, which is the prototype thermal reactor as opposed to the electric power reactor, which is so-called ARC. Spark is basically a direct scaling, essentially, of Alcator CMOD. So the pressure has been achieved also, temperature's been achieved. There's something called the Lawson Criteria. I didn't go into that today because I want to kind of focus on confinement as the starting point of the next talk. The Lawson Criteria is basically going back all the way to the solar stuff. The fusion reactor has a core where it's very hot and where fusion is happening, and then there's the surrounding area where radiation is carrying away the energy. And that radiation is not the neutrons. That radiation is radiation in the form of photons, because of the fact that there's always going to be some non-ionized material there, and it will basically emit radiation. And if you operate at the right temperature range, there is then a product of this density and confinement time, so that more energy is being produced in the core than is being radiated away. And that's the so-called Lawson Criteria, and that comes in slightly different versions for slightly different situations. But the net result is you end up with this kind of a device. The core is a small volume of this thing in here. This rest of this is plasma that you have to confine. And this is the reason you have to confine it, is because these walls in the early experiments were cooling things. They still cool things, but now there's enough energy density potentially here that these things can start to cook. So that's been the problem with the process of going from the laboratory curiosities to the big prototypes almost of a reactor. The one other uncertainty in the whole thing is that, and this is a sort of a technical detail, but confinement so far has been studied predominantly with protium hydrogen, some deuterium hydrogen, and occasionally some helium that's been added to the system, but never with fast alpha particles. Those fast alpha particles could throw a curveball that we don't know about. But all of what we understand so far, it looks like the physics is understood well enough to get us to, if we have tritium, to produce net energy with the superconducting magnet. Breeding the tritium, that's another issue, because you have to make sure that you don't lose too many of the neutrons on the way to breeding the tritium and stuff like that.
Thanks.
Barry?
Now, I want to go back to the issue of what was wrong with the cold fusion studies. And I went back and I took a hard look at Michael McCubre's paper, in which he claimed that the thermal energy coming out of his electrolytic cells exceeded the electrical DC power going in. And he made a simplifying assumption that he did a hand-waving argument. He asserted that the Faradaic current was pure DC with absolutely no AC perturbations or AC component riding on top of the DC. And he left it out of his energy budget model. And I looked at it and I said, you can't do that. If you assume that there's no AC riding on top of the DC, telephones wouldn't work. Your classical analog telephone, the energy you care about is the AC, the voice signal in case of a telephone, and you get that out of variable resistance. So I went back and I did a pretty simple calculation of the amount of AC, what you would call burst noise or shot noise or hiss from perturbations in the resistance in the cell, and it exactly accounted for the excess thermal energy coming out. And if they had put an ordinary audio VU meter across the cell, they would have seen that VU meter register the amount of AC energy going into the cell that he was leaving out of his model.
Well, there's a lot of speculative stuff going on in terms of the data that's been collected and presented. And it ranges from people who, are claiming they have a back to the future kind of environment almost, to people who are much more restrained about their claims, let's say, and, who've tried to do a fairly careful study of things as they can. Now, the problem is that, it involves so many different disciplines. You have to deal with the materials, how the hydrogen gets into the materials and stuff like that, how the hydrogen might come out of the materials, other things. If you do see helium, where is it coming from and how's it coming from? And then, all the thermal issues and balancing things. And, I think at this stage, as I said, there's some effects, but it's a long ways from being a practical thing. That said, there are people who claim it can be achievable inside of 10, 20 years time frame also. Maybe so, but they haven't really proven it certainly to satisfaction of the majority of the scientific community at this stage, I don't think. I wouldn't dump it as an impossibility, because obviously crazier things have happened. When people started saying you could see flashes of light from cavitation bubbles in water, everybody said that was nuts, but it turns out it's real. Highly nonlinear phenomena are, pretty exotic stuff.
Well, the good news is there's a small subset of us that'll be here to understand what's going to happen in 30 years.
Yeah.
So, we don't have to worry too much about that. Mike Alexander.
Yeah. Okay. The power is going to be extracted from the neutrons. How?
Well, when you absorb the neutrons in this blanket, and there are any number of different schemes for blanket design, you basically produce heat in the blanket as a result of that neutron capture, production of tritium, production of helium. Everything that comes out of that reaction is an energetic particle, and it just bangs into the lattice of some silicon dioxide sponge or something, or whatever, different types of supposed ways of handling some liquid lithium. But you have issues with liquid lithium with respect to the how you move it around in the strong magnetic fields and things like that. Depends on the different types of reactor sort of designs, put the blankets in different places and use different materials. But the net result is you run water through eventually, and you end up with steam, and you have a steam turbine.
What about radiation damage?
There is some radiation damage, not to the blankets per se, but to the so-called first wall, which I don't know. Do we have a picture of the thing here? Yeah. So this stuff right here is what's there to essentially protect the vacuum vessel on the inside. And it's made up of materials that could be as low atomic number as carbon, as high atomic number as tungsten or molybdenum. There's certain different arguments about how to do that and what the effects of that is. But the net result is beyond that, there is a vacuum vessel. And this material, you expect it to be damaged because, you know, that's okay. That's the reason the material is there. It's a shielding material, but the vacuum vessel, you'd like to stay intact. And some designs, like an ITER type of design, it would be very difficult to replace segments of the vacuum vessel, and because of where the magnets, what the magnets enclose. And in other designs, like the ARC design, segments of the thing can be taken apart easily. In any event, you have to plan for at some point or other dealing with the various kinds of neutron damage. The problem with the fission fusion hybrid, comparison and fission and fusion comparison in a sense is that in a fission reactor, you produce your energy in the core, and you take the energy out of the core directly with the circulating water or whatever. There's incidental damage to the confinement of the core in the reactor vessel, and you can accommodate that by keeping that relatively hot. And so while the neutrons are banging into the iron atoms and stuff like that in the steel, you can anneal it continuously. Essentially, the neutrons are much less energetic as well by the time they get to the actual reactor vessel in a fission reactor. In a fusion reactor, you produce the energy in the core, and the energy comes out through the surface. So the more compact you make it, and the higher energy density in the center you make it, the more potential issues you have to deal with the damage of the so-called first wall. And there's some predictions that you might knock every iron atom, if it's stainless steel, essentially every iron atom would be knocked out of its place in the lattice once a month. Now, how long can that go on before you have to replace it, or you have to anneal it, or something else that you have to shut your equipment down to do it? Nobody really knows yet. That's kind of the engineering kind of stuff that still needs to be really looked at.
Charlie?
Yeah, I'm thinking about fusion as a source of energy. All of it is extrasolar. I mean, it has nothing to do with the sun. So in effect, you're generating all this energy, which eventually becomes heat and is added to the heat that the sun delivers to the earth. At what point do we find that climate change is actually being caused by this heat overload?
Well, I think we have to go ways before we get to that point. If you look at what the solar advocates are saying, we can generate all the energy we need for the entire planet with, just covering Nevada with solar cells or something like that. So the amount of sunlight actually falling on the Earth and heating the Earth, the atmosphere and the surface of the Earth is a lot more than what we generate, except, locally, obviously. We can produce a lot of energy density in a very small spot. And, but by comparison on an average, scale, you're talking about a very, very small amount of energy that's actually being involved in, unless our demand for energy grows by many orders of magnitude. I don't think we worry about that too much.
I mean, we can actually put numbers to both of these things. That is, we know what the world generation of certainly electric power is.
Yeah. We have numbers for the total electric generation right now, and we estimate some of these other thermal things that are not electric that are part of our energy budget, and there are numbers you can get from the energy it's a DOE department, or DOE agency, Energy Information Agency or something like that. I don't know. They produce copious piles of these kind of reports and stuff. And there's big numbers that are there, and those big numbers have some uncertainties to them and stuff like that. But yeah, you can get those numbers. But the relevant point is that nobody is looking at current energy consumption rates being relevant to the amount of energy coming from the sun. It's human consumption of energy is pretty small by comparison right now.
Ted, I'm going to ask the inverse of Charlie's question. I thought somewhere in your presentation you glossed over endothermic nuclear reactions.
Mm-hmm.
Sure. Is that a viable heat sink?
Well, of course, in principle, you can do endothermic reactions that suck heat out of a system, and convert it into matter, essentially. I mean, that's E equals mc squared, right? So if instead of having a net positive 20 MeV, you have a net negative MeV, 20 MeV coming into your reaction, and you end up with a nucleus that you carry off that has that 20 MeV in the nucleus, instead of it being thermal energy coming in. Yeah, you could, of course. I don't know of anybody practically pursuing that line of study, though. I'm sure there's perhaps somebody's written a dissertation on it or something like that.
Oh, giant worldwide refrigerators.
Yeah, absolutely.
Exactly. Put one of these things in the Antarctica and see what happens to the ice.
Yeah. Well, you could you could probably freeze some ice if you wanted to. I mean, I perfectly happy right now with my problem I have in my freezer in the basement. It's doing a very good job of freezing water out of the air. I don't know where it's getting it from, but it's producing a traditional icebox effect inside the freezer, which should not be there, but it's
check the seals along the door.
That's what I was told. Somebody said, yeah. It doesn't have to be a very big leak, apparently, but
no, especially when it's humid.
Yeah.
Bob?
Just with regard to endothermic nuclear reactions, there probably would be more of an effect if there were a way to take carbon out of the atmosphere and fix it in a useful way, maybe even in a productive way. That's also being worked on. Just a little sidebar on that.
Yeah.
Yeah, and the other thing that you have to deal with, in the sense is, in most cases, and you can get into a long discussion about these things, but in most cases, the human effect on the atmosphere is a local effect. You see it in the scale of hundreds of square kilometers, thousands of square kilometers in some cases, perhaps, but not in millions of square kilometers. So you have the ability with ample supplies of energy to move, heat pumps and whatever on a big scale. You could move energy that's overly concentrated in a particular place and disperse it, for instance, in various ways. So once you have available energy, you can do a lot. And I think our biggest mistake, if we don't pursue things like fusion, in a aggressive fashion, is that we're missing all the benefits that come from what you can do with electric energy. And then, also there's some thermal energy that could be useful from a fusion plant also potentially. But it gives you something that you can't really do if you get rid of all the coal-fired power plants, you get rid of all the natural gas-fired power plants. You're talking about most likely needing very large amounts of area. Maybe it's on shore with the deserts and whatever with solar arrays, and maybe it's offshore with wind turbines, but a lot of land and potentially sea surface that's needed to be devoted to generating energy. Whereas, if you have a compact fusion plant, if if it's the size of, I don't know, let's say in Lexington, maybe the Monroe School, something like that, maybe smaller than that, a little bit footprint. You can put that pretty much anywhere in the city.
This was really great. Thanks.